don't know what happened. Thank you for the warning. Appreciate that. Well, too bad today's video will be. You know what? I'll see if I can find an old stereochemistry video. Would you guys mind if I upload the 128A video here? It's very similar discussion. So I think I'm going to upload the first part of 128A video. I'll write some notes, so don't freak out. So use that, and whatever we record today from here, I'll upload that too. I'll call both stereochemistry 1 and 1 prime or something like that. Sorry about that. I should have noticed. It's usually, see, this is why Zoom is not totally 100% reliable. Thank you. I'll upload the other video, and it's very similar. I usually start with this strange objects and then go to chemistry, the real molecules. Any questions so far?
No.
No, you're good. This is kind of sinking well. It's you guys are understanding. Now, why this is important when it comes to molecules? Why is this important? Why do we bother? Why do we care about stereochemistry of molecules? What do you think? Why do you think it's important? Do you think the molecules can have this symmetry problem and then they can exist in two forms, lefty or righty? Can that happen? What do you guys think? I'm going to scoot back to the side so that you guys can see the board. Do you think it can happen with a molecule?
I think so, like methyl groups being on different sections, kind of like that. Or
basically a molecule losing its symmetry. A molecule can be symmetrical if a molecule loses its symmetry. The moment a molecule is not symmetrical, then its mirror image and itself, the molecule, they will be different species. There will be one will be lefty and one will be righty, right? We'll talk about that. Why this is important? Why do you worry about a molecule being a lefty or a righty, like my left hand and the right hand? From your perspective, this is my left hand, but I'm calling it my left hand because it's easier for you to kind of perceive.
It'll change the polarity of the molecule.
Yeah, to some extent. Well, polarity is going to be like, if I have a fluorine here and a carbon here, it's going to be pulling that direction. It's going to be pulling that direction, the two molecules. Something else, like we talked about wearing shoes, the right shoe for the right foot. We talked about shaking hands with somebody else. So in the living system, right? In the living system, when you take Tylenol, I don't have Tylenol here. I have Tylenol in my wallet, but I'm not going to waste it. Tylenols are very precious for me. I get headache once in a while. This is ibuprofen. Okay, this is not Tylenol. Tylenol, let's take three examples. Tylenol, aspirin, and ibuprofen. Okay, there is something special about ibuprofen. Not because of that I keep it here. It's been sitting there. I had some major back problem 2020 December, 2019 December. It was so bad that I had to take ibuprofen to reduce my inflammation in my lower back. So it's been sitting here since then. This guy is different than Tylenol and aspirin. What do you guys, you want to take a wild guess what's different for ibuprofen with respect to Tylenol and aspirin? Anybody wants to say? So let's say this is Tylenol, this is aspirin, and this is ibuprofen. What's so special about ibuprofen? It has something to do with the discussion we are having right now in the class.
Is it symmetrical?
It is not symmetrical. Tylenol and aspirin are symmetrical, Fernando. This guy, ibuprofen, is not symmetrical. I'll draw its structure a little bit later after introducing molecules, okay? So if ibuprofen is not symmetrical, what do you think can be a problem or a challenge when you're developing ibuprofen as a painkiller or an anti-inflammatory agent. What do you think happens when you eat a molecule and it goes inside your bloodstream and it gets absorbed through the tissues and goes to the different cells? And how does it reduce your pain? They're not just sitting there, right? I mean, this is what makes medicinal chemistry so fascinating. Biological chemistry or biochemistry is so fascinating. You know, making just a molecule, is cool, could be rewarding because yeah, oh, I can put a bromine and a chlorine and a fluorine and a methyl group together and I can make like a really cool molecule. There was a time when you could ask for funding just to make a fancy, cute, literally, I'm not kidding. You could make like a really interesting molecule and you could get funding for like $300,000 for 3 or 4 years to make those compounds. But those days are gone, right? Now we care about what this molecule is going to be good for. Why should NIH pay me $400,000 to burn in 4 years to get what? How can it help human beings? Can it be a cancer drug? Can it be a pain drug? Can it be an Alzheimer's disease drug? Can it do something in the agricultural field? Can it repel like some pests? Things like that, right? Can it work like a fluorescent tag for measuring tumor growth in the body? All these things, right? So then you get funding, right? So making a molecule is important, but then figuring out what actually happens to the molecule in the living system is different. So Tylenol, aspirin, ibuprofen, they all interact. They go inside your blood, you drink it with a glass of water. It gets into your intestine, goes into your stomach, gets absorbed, then the coating, I'll waste one molecule. One of this, not molecule, one tablet, one capsule, right? So if this is ibuprofen, right? The coating and the stuff inside, the kind of like the bluish green, material that you see inside, that's not just ibuprofen. Ibuprofen is a molecule. It's actually an aromatic molecule, and it happens to be a safe aromatic molecule. There is nothing wrong with this molecule. All this stuff is like your bun and your lettuce and the mayo and all this stuff. This is called formulation. The pharmacists, like many of our students want to be pharmacists in this valley, right? That's one kind of pharmacy, retail pharmacy. The other kind of pharmacists, they're research pharmacists, they actually figure out how to work with the molecule and how to make it like how to give it like a shape or form that humans can take as an oral medication, right? Once you eat it, it goes inside your in your intestine, and eventually the coating falls off. It gets eroded. The other edible parts, it could be some polymer like sucrose or glucose or other edible polymer or other compounds that it's mixed with that helps it. That package is important. It's called formulation. Eventually, the molecule, the organic molecule, the ibuprofen molecule will get out of the system and goes into your bloodstream, gets absorbed through the wall of your intestine and your short intestine and long intestine and your gut, and then gets into the bloodstream, starts flowing to different body parts, and eventually it'll interact with certain proteins. They're involved in the synthesis of pro-inflammatory objects, such as they're called leukotrienes. Leukotrienes are, they're called, what's the other word? I can't remember right now. Leukotrienes and prostaglandins. Okay, you may have heard COX inhibitor, COX, cyclooxygenase. There are proteins that they're like little catalysts. They're helping synthesize different molecules in the body. What ibuprofen does, it messes up at one point it binds with, like, let's say there's a multi-step synthesis. Step 1 to step 2, A becomes B, B becomes C, C becomes D, D becomes E, E becomes F, the final compound. And what is the need for the compound? Its job is to increase inflammation. So let's say I bump into a lot of things. If I bump into the wall on the let's say I accidentally run into the whiteboard and I bang my knee. I mean, not knee, my elbow. What it does, if there's an injury, body starts putting pro-inflammatory agents dump here. It's basically like, you know, you screw up something in the wall and you try to put some mud, some soil, some, you know, some like some kind of glue, and you're trying to fix it by, you know, like by putting some materials to kind of temporarily fix it, like a Band-Aid fix. When the road has cracks, you will see that the road workers will come and dump different kinds of like tar and molten tar and other materials to basically fix it, basically fill it up. So inflammatory agents, pro-inflammatory agents are important for our body to heal, because if I bang my knee and you will find that it's got swollen. How does it get swollen? Because its body is dumping all kinds of inflammatory agents there to fix the problem, and slowly the inflammation goes away. So one way to handle pain is by reducing inflammation. So what this molecule does is it interacts with a protein. It's called cyclooxygenase, COX, COX-1 and COX-2. You may have heard the word, like Pfizer is trying to develop a COX-2 inhibitor or COX-1 inhibitor. What is COX doing? It's in that multi-step synthesis of making something that causes inflammation. You are basically messing up one of the 5 steps. This guy is going in, and let's say it's messing with the second step, where this catalyst protein is doing its job to convert B to C. Then C gets converted to D by somebody else. D gets converted to E by somebody else. You are basically using this guy to go inside your body and mess up with the second step. If your second step is messed up, you don't make so much pro-inflammatory molecule, prostaglandins and leukotrienes. As a result, what happens? Well, body doesn't get inflamed. So you reduce inflammation throughout your body, sometimes more in the brain, sometimes more in the gut, sometimes more in the backs. That's why different medications have different purposes. If you have a headache, for me, Tylenol works better. When I have lower back pain, ibuprofen works better, okay? And the mechanisms are slightly different. So with this long convoluted story, why is it important that we understand the symmetry of a molecule such as ibuprofen? Why is it important? And when it's because it eventually boils down to the fact that this guy, after I eat it with a glass of water, it goes in my body, goes to the gut, gets into the bloodstream, and reaches different body parts. And it basically is trying to mess up some biosynthesis of some inflammatory molecules by screwing up one of the multi-step synthesis. And it's doing that by binding with a protein. And that proteins are made out of amino acids, and each amino acid except one, there are 20 natural amino acids, except one amino acid, all of them have this lefty and righty property. Actually, our bodies in this world, most of the amino acids are made one way, lefty. Let's call it lefty. They're not righties. So sometimes we joke when we were learning proteins and amino acids that, is there a parallel universe which is made by the other type of amino acids? Wouldn't that be pretty cool? I mean, how would we interact with each other? Probably it'll be a bad idea, right? So our body is made out of proteins and DNAs and RNAs and enzymes. Enzymes are special proteins. Receptors are special proteins. They're all proteins made from the combination and permutation of 20 amino acids. You put one, then you put another one, and you put hundreds of them, and that sequence determines their shape and property, right? So imagine a protein is made from only lefty amino acids. So that means when ibuprofen is going in to basically bind with that specific protein, cyclooxygenase 2, do you think that both lefty ibuprofen and righty ibuprofen will interact the same way, or one will be working better with the protein? What do you guys think? There are two ibuprofens, right? One is a lefty, the one on the left side of the mirror, and one in the one in the mirror image, right? One is this and one is that. The ibuprofen that you have in there. One is left, one is right. When they're going in to bind with that protein cyclooxygenase, which is also lefty, let's say lefty, because they are made from one type of amino acids. All the 300 or 400 amino acids, they're all lefty, so they have certain property. So there is also lacking, symmetry is lacking, right? So do you think that both left ibuprofen and right ibuprofen will interact the same way, or there will be a little difference? One will be doing a better job. What's your gut feeling? What's your opinion?
I would say differently.
Anybody else? I'm going to throw away this ibuprofen. I've been touching it quite a bit. Anybody else? So the left ibuprofen and right ibuprofen, should they interact the same way with somebody else, a bigger molecule that's got, it's also like doesn't have symmetry because of, sorry, go ahead.
They're gonna act differently because it's gonna bind with the other one who's also different. So one's gonna fit better to the left of the other versus the right of the other.
Anybody else? Is this concept syncing with you guys?
Yeah, I would agree with what's been said before, and going back to how you said that aspirin doesn't have the same effect on those proteins, and you said aspirin is not, or is symmetrical. So there's something about the asymmetry of ibuprofen that allows it to bind with those proteins that other drugs don't have the same capability of.
You guys heard Craig and Daniela and somebody else, Danielle? What do you guys think? The rest of the class, what do you guys think about this discussion? Do you think this is important? I'll tell you why it is important, and I want you to do a Google search after we hang up from this class. What do you guys think? So this is an important thing, right? But I just want to highlight something Craig mentioned, that aspirin cannot bind. Just because I have symmetry, like if I'm aspirin or if I'm Tylenol, and if I have symmetry, that doesn't mean I cannot bind. I can still be able to bind, right? Ibuprofen happens to be not having symmetry, and it can exist in one or the other form, this side or that side of the mirror, right? That doesn't mean aspirin is also binding with another protein. Tylenol is also binding with another protein. It's just a symmetric object binding with a bigger object, bigger protein that's got no symmetry. Okay, they can still bind. It's fine. Many compounds, many drugs are symmetrical. DEET, the molecule that we spray to chase off mosquitoes, that's another project that we're working on. That's symmetrical. It's got some problems. We will talk about it maybe toward the very end of this class. Remind me about DEET when we talk about carbonyl chemistry. It's got another aspect of organic chemistry, which is very cool too. So the bottom line is, if your molecule, such as ibuprofen, has this symmetry issue, you have to be careful, because what if the lefty works and the righty doesn't work? That's exactly the case with ibuprofen. Okay, it's not a big deal. The righty, it just sits there and does nothing. It cannot bind, because you cannot shake hands with someone's right hand with your left hand. So this guy just stands there like an observer. It's not doing anything. You cannot shake hands with your right hand and your left hand with same efficacy. It's going to be pretty bad. This is going to be a disaster. Okay, if I grew up in a jungle with monkeys, and if I'm trying to shake hands with a gentleman, you know, wherever I am, I might stretch my left hand. I mean, that could be somehow, you know, that could be a movie plot, right? Like, why is this guy bizarre in the civilized society? Because he doesn't know which hand to use when it comes to shaking hands with somebody. Okay, he's stretching his left hand and maybe putting it the wrong way, right? So it's important. It's very important. For ibuprofen, it's not a big deal. For this molecule, Google it later on and then tell me what you learned from it. I usually talk about it, but I'm not going to talk about it. I want you to Google it. There is no points attached. This is just for fun. Thalidomide, Thalidomid. Unless somebody already knows the story from the 1960s, you can share it. But the bottom line is, it's very important that the molecules have, if the molecule has a symmetry issue, then you better push the right molecule as your drug. It's kind of funny that our Alzheimer's disease project, when we had first identified 5 molecules that we thought are pretty important, should be developed further and should be pursued further. It turned out that out of 5 lead molecules, 3 of our molecules had this symmetry problem. They were lacking symmetry. So we had to make the left guy and the right guy for that guy, left and right guy for this guy, and left and right guy for this guy. And we separately tested them as pure lefty or pure righty. And then the research is ongoing right now. It's very important. So I'm going to pause for maybe another 30 seconds, and then we're going to get into the molecular world and see what does a molecule have to possess to have this special property of being non-superimposable on its element. And what are those guys called? Okay, just stare at the board for a few more seconds. I'm going to use the same board, so it's going to be just one picture today, and I'll get into the molecules. Like, what do we have to have in the molecule to have this specific property? This is fascinating. It's very important, and you cannot run away from stereochemistry because we are made out of molecules that don't have symmetry, unfortunately or fortunately. Any questions, any comments, any concerns, you can share it right now. And I'm once again, I'm sorry about that recording issue. Something went wrong. All right. So now let's get into the, yeah, go ahead.
Yeah, I just want to let you know, I think it was recording. Like, I started recording a while ago too, so I don't know.
Yeah, because I pushed the button.
Oh, okay. Thank you.
Yeah. So let's get into the molecular world and let's see what does it need to have. I mean, how can we screw up the symmetry? I mean, if you understand symmetry, life will be easier. But if you just want to remember like something in the line of kind of like memorizing stuff, then that's fine too. Okay, just give me a second. Okay. All right, so the symmetry business doesn't work with sp2 carbons or sp carbons. Okay, it has to be an sp3 carbon. And since I do not have enough blue sticks, I have to use black sticks to describe it's a what do you call hydrogen. So let's draw a methane molecule. Okay. Let's draw it here. There is a methane molecule here in 3 dimension, right? and I'm going to draw its mirror image on this side in 3 dimensions. The question is, when you have a methane molecule, it's got an sp3 carbon in the center, okay? It's got some depth in it. It's a little chubby molecule. It's not just a flat molecule, okay? So there are 2 molecules. Why is my methane looking kind of distorted? That's fine. I think you guys understand, okay? So these are the 2 methane molecules, one on the left and one on the right. And they're all hydrogens. Imagine they're at the tip of the stick, there is a hydrogen here, right? Now, if I try to superimpose one inside the other, one on top of the other, what do you guys think? Do you guys think they will be superimposing one on top of the other, or it'll be difficult to superimpose? It's not a trick question. Just answer what you have in your at the tip of your tongue. Superimposable, yes or no? Say something, please, because I'm just looking at the camera. Yes or no?
Yes, they're
Yes.
superimposable.
Yeah.
Okay, so let's try that. Okay, let's see if we can superimpose. Absolutely. Everything lines up, right? So they're superimposable and they're mirror images. So I'm going to just write down on the right side. They're mirror image and they're superimposable. Okay, now let's start messing with the molecule by changing one hydrogen with something else. Let's try. Why am I drawing S? I have no idea. Let's keep this hydrogen. Let's keep this as a hydrogen. Let's change one thing here. Let's change this top guy to a fluorine. That's a chlorine, okay? So let's change one of the sticks to a purple chlorine. Purple means chlorine, okay? 902. Okay. If we can accomplish this today, that'll be great. All right, so that guy and this guy we are comparing, right? So how does the molecule look like? Okay. Okay, 3 hydrogens, hydrogen, 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 3 hydrogens at the bottom, and a chlorine, right? Do you guys think they're superimposable? Yes or no? Yes. Can
Yes.
you? Okay, somebody says yes. That's probably Michael. Anybody else? Yes or no? Superimposable?
Yes.
Okay, yeah. It's easy. You can line them up. Slightly bent. Okay. Superimposable. They're lining up. So again, this set, that set and this set, they're mirror image and they're also superimposable. So there is no drama going on with them. They're identical compound. They're like ibuprofen. They're not like ibuprofen. Both the compounds are like Tylenol or aspirin. Let's change one more thing. Let's make these 2 hydrogens. And where is the mirror? It is the mirror. Let's extend the mirror. And here. This is our this is the chlorine. And let's change the other guy, this guy, to a bromine. I like halogens sometimes because it's easier to fathom. Okay, and this is a hydrogen, not a methyl. Let's move this molecule a little bit out to the right because I want to draw the last molecule down here. So it's going to be here. Hydrogen, back is also a hydrogen. Up is a chlorine. And on the right side, there is a bromine. Okay, let's make the model and let's test if they're superimposable or not superimposable. These are the two molecules. Chlorobromomethane. Okay, this is the molecule on the left, this molecule, and that's the molecule on the right. What do you guys think? They're superimposable or not? If I try to put the purple on the purple and the red on the red, will the blacks match?
Not without rotating one of them.
Yeah, but rotating is not changing the molecule. Rotating is just looking at the person from the back or the side, right? Yeah, so if I rotate and if I do this, what do you guys think? Should you call them superimposable?
Yes.
Yes. Okay, so this couple is also mirror image and superimposable. So no drama going on. Why is it so? Well, because I need something. Because if you think about this plane, what's written here? Is it important? No. I'm going to tear the page. If I use this plane, the plane that contains the central carbon and the chlorine, a bromine and the chlorine, you will find that it's a plane of symmetry. Okay, because the two hydrogens are sticking to the right and the left, and it's a plane of symmetry. So there is a plane of symmetry along this surface that contains the bromine and the chlorine and the bromine and the chlorine and the central carbon, and with the flanking hydrogens on one on the right and one on the left, because it's got symmetry. Okay, now finally we are coming to the conclusion and the climax of the story. Let's change one more atom. Let's go with the hydrogen. Hydrogen is going to be remaining in the back. Okay, the chlorines are on the top. Bromines are on the right and left. And let's put a fluorine out. That's a fluorine, a green fluorine. Okay, let's change it. All right, so this guy will get a fluorine here. Okay, so that's the molecule: chlorine, bromine, hydrogen. That's a fluorine. For this molecule, chlorine, bromine, hydrogen in the back, this guy is going to be the fluorine. All right, now tell me, now the business, sorry, I was holding it the wrong way. Okay. Now this molecule has a central carbon, and the central carbon is holding on to 4 different things around itself. Each corner of the tetrahedron is different. Hydrogen, what is that? chlorine, bromine, and fluorine, right? Sorry, holding it the wrong way. Do you guys think the molecule has any symmetry? And do you guys think that the molecule and its mirror image, they are superimposable or not? What do you guys think? We will do that exercise in a second, but I want you to kind of jump and give me some answer.
They're symmetrical, but they're not superimposable.
Where is the symmetry? Is there symmetry along this plane? Are the left and the right same? Is this symmetrical? You have a hydrogen on the right and a whatever that is, fluorine on the left. It's not symmetrical. Let's check another plane. This plane. Is it symmetrical? Nope. Left and right are different. Let's try another plane. There is no symmetry. It lost its symmetry last time when you swapped it with the fluorine. As long as there were two hydrogens, it was symmetrical because this was a hydrogen, left and right were same. But you replace that last symmetrical hydrogen with a fluorine, now you messed it up. There is no symmetry. Okay, so the first thing to take is there is no symmetry in the molecule. There's no symmetry in the molecule. And the next question is, if I try to superimpose the two molecules, one on top of the other by lining up the colors, do you think I'm going to succeed, or do you think it's going to be an epic failure?
You won't be able to do it.
I won't be able to do it, Danielle?
No.
Anybody else?
Yeah, it won't work.
It won't work, Michael? Let's try. Let's try to match the purple and the green and see what happens. Well, if I try to match the purple and the green, oops, the red and the black, they don't match. They don't superimpose. Try to superimpose the red and the black. Okay. Yeah, I succeeded red and the black. Oops, the purple and the green, they don't match. Let's try red and the purple. Red and the purple, I matched, but the black and the green, they don't match. So the bottom line is, when an sp3 carbon is attached to 4 different things, the molecule and its mirror image are not superimposable. Let me write it down. So this is, the relationship is their mirror image not superimposable. That's the kind of carbon ibuprofen has. Because of it, it has developed this characteristics that it exists in 2 forms, lefty and righty. Aspirin and Tylenol, they don't have that property. So when you have 2 objects or 2 molecules that are mirror images, we have 2 more minutes. When you have 2 molecules that are mirror images, but not superimposable, they are 2 stereoisomers, lefty and the righty, okay, which we cannot label them as lefty and the righty. Okay, one is one way, another one is the other way. Okay, and the specific stereochemistry term to describe their relationship, it's called, anybody knows the word? It's an E word. It's called, no? So when you have 2 compounds that are not superimposable but mirror image, they're called enantiomer. I think that will be the last message that I want to send today. So 2 molecules, 2 mirror image molecules, not superimposable, are I'm going to write it down again on Thursday. Enantiomers. It's kind of crowded, I understand, but I'm going to go over it one more time on Thursday. Two mirror image molecules, they have to be mirror image, that are not superimposable are called enan, E-N-A-N, enantio, Mars, enantiomers. They are one kind of stereoisomers. So these two guys, their relationship is enantiomers because they're not superimposable, but they're mirror image. My two hands, if they were mirror, they were molecules, their relationship is enantiomer. Enantiomers. My kidneys, enantiomers. Lungs, enantiomers. My feet, enantiomers. My knees, my elbows, they're all enantiomers. I think with that, let's finish our discussion today. We'll catch up on Thursday, and I think I'm planning to finish it by Thursday. Okay, and then we will talk about substitution reactions and carbonyl chemistry, and that will probably bring us to the end of our chemical class this time. Okay, I'm forgetting something, taking a picture. And I will be uploading a Chem 128A video from Stereochemistry. So don't freak out, I'll leave a little note there. And once again, the message that I sent to all three classes about Chegg and chain problems, that I didn't mean that to send it to you guys, so ignore it. Okay. Have a good day, have a good Tuesday, Wednesday, and I'll see you guys on Thursday. Okay.
I just had a quick question. Sorry.
Yeah. Go ahead. Let me move to the front camera.
Yeah, I don't think my camera is working at all.
No, your camera is. Yeah, that's fine. Don't worry. Don't worry about that.
What did you say about when the sp3 carbons? You had said something about that.
Yeah, it has to be an sp3 carbon, and this property can be only developed by molecules that have sp3 carbon, because you have to have 4 things attached to the central carbon to kind of lose your symmetry. So if you have an sp2 or sp carbon, we will discuss it on Thursday. Don't worry about that, Danielle.
Okay, thank you.
All right.
Bye.
All good.
Yeah,
All
thanks.
right. You guys have a good day. Continue to stay safe, and see you in less than 2 days. Bye, Matthew, Judith, Danielle, Craig, Vanessa.
I got a question for you,
Yes.
but it's unrelated to this lecture. If you want to pause the stop recording.
Yes.
Okay.
Stop. Hold on. Let me stop recording. Do you want to stop cloud recording? Why is it cloud recording?